Hello and welcome. So with the video, we're talking about the Solow model, and we're talking specifically about transition dynamics. And I'm working in the context of like the full model with technology and population growth. So first of all, the other things in this video is one of many covering the Solow model, particularly like the nitty-gritty stuff that professors don't usually like to cover in lecture. So check out the video description if you want to check out those other videos, or if you want to skip ahead to these topics. We're going to talk about in this video how like you could expect many different shocks, right? So there's a number of exogenous variables in the Solow model, like the savings rate, growth rate of population, growth rate of technology. There's the depreciation rate. You could conceivably destroy capital stock or bring in quite a bit of extra capital stock. The question is, how do things evolve through time, right? The Solow model is a dynamic model in that there's a capital accumulation equation, the law of motion equation, law of motion of capital equation, and it describes how capital evolves through time, and that feeds into pretty much everything else. So given these shocks, some of these shocks might result in an instantaneous change in some variable you care about. If you destroy capital, obviously capital stock, part of this capital stock is instantaneously gone, but also some things evolve through time. That capital accumulation equation describes how things like the capital stock and others are going to slowly change period by period by period. So the question is, well, when you shock something, is that instantaneous effect? Is it, or is it something that changes through time? And then when it changes through time, there's actually different effects you could have. And then I'm going to classify them as level effects and growth rate effects. So to make that point a little bit more clear, let's look at one of the summary tables that I had from a previous video. So in a previous video, we went through and calculated growth rates and what shocks kind of the major variables of interest. So up here we have capital and output per effective worker. So per effective worker, right, you have A, which is labor augmenting technology, and L, which is the labor stock. In this section here, we have our per capita stuff. That's the lowercase letter. So capital per worker, output per worker, and then investment and consumption per worker. And then down here, we have all our kind of aggregate key variables. So labor, capital, output, investment, and consumption. And in those previous videos, we kind of summarized these two columns over here. So we define the things that affect the growth rates of each of these variables, and we define the things that affect the level effects of each of these variables. So let's go with kind of a simple, easy example. Let's think about a change in the savings rate, right? So suppose we instantaneously increase the savings rate. What effect does the increase in the savings rate have on all of these key variables? So we see that the savings rate appears pretty much for everything in terms of level effects. And then for a few things, investment and consumption here, it changes things for an instantaneous change. So for example, take consumption per worker. If we were to increase the savings rate instantaneously, like, so today the savings rate was, 10%, and tomorrow the savings rate is 20%, let's say, consumption would instantaneously jump down, because this number, consumption, just takes output per person and multiplies it by some number that's 1 minus the savings rate. So if this savings rate went up instantaneously, then you expect consumption to drop down instantaneously. But also, there are these level effects. So I think a key way to look at it is to turn to our Solow diagram model, which I'll get to even lower, kind of steal my thunder. Okay, here we go. So here's the Solow diagram. What happens if we increase the savings rate? So the savings rate appears here in the investment curve. That's the red line right there. If the savings rate increases, we know that this line shifts up. That red line is going to shift up, and it's going to result in a new steady state level of capital per effective worker, right? So that this K star here is going to jump up to some level up here. Let's see. Well, Wolfram Alpha has a nice little demonstration thing. So if we started off at this savings rate right here and we increase it, we see this light blue line shift up, and we see the new K star at a higher level, right? So you were here, and now we result in a K star, a steady state level of capital per worker there. However, the stock, of capital per effective worker does not change instantaneously. That's the main point of this whole thing. There's kind of like a dynamic process that evolves through time. that describes how it happens. And I have gone through the process to draw that for you. So with this graph right here, we see this is consumption per worker, right? So instantaneously, let me line this up. Okay. This gray dotted line is the instant when the savings rate increases. And so we're looking at consumption per worker. So the moment the savings rate increases, that results in the drop in consumption per worker, because when we're looking at that equation, consumption per worker was like this instant, the function of the savings rate. So if the savings rate jumps up, then instantaneously consumption goes down. However, savings also had a level effect on output per worker. So what do we mean by level effect? Well, we mean that if we were growing at some rate before, a level effect is we've shifted that level up to another level. So we were at this level, the increase in the savings rate shifts that level upwards and to this new level. However, that doesn't go instantaneously, right? So this is capital per worker. Capital per worker has this slow evolution upwards. However, consumption per worker, because consumption's a function of 1 minus the savings rate times output, has an instantaneous drop. Output per worker, you can see we were at this lower level here when the savings rate was lower, and then at this moment in time, right where that gray dotted line is, we have the new savings rate, so we have a jump up to the new steady state level of capital per worker. However, that steady state level of capital per worker doesn't occur instantaneously. It takes time for capital per worker to evolve up to that level. And so we see this level effect, and it's a slow accumulation of capital per worker increasing. So those are level effects, right? I've done it down here. We have output per effective worker. Similar here. Here's just total output. Here's total capital. You can see these are all level effects. But let's think about it. Well, what happens if we shift something that changes growth rates? So here's our little summary. What here affects growth rates? Well, things that affect growth rates are things like population growth and the growth in technology. All of these variables are affected by the growth of technology. That's what we have G in our notation. And all of these things here are additionally affected by the population growth N. So let's see what happens when we increase the population growth on our time series graphs. So if we were to increase population growth, right, we would expect all of these variables, the aggregate levels of labor, the capital stock, aggregate output, investment consumption, we expect all of them to grow at this new higher rate. We also don't see any level effects. So let's have a look. So here I've drawn time series graphs where we increase the savings rate. So we increase the growth rate of population. We can see right at this moment, that's at the dotted line is where I increase the growth rate of the population. So before population growth I had a 0, and after this population growth is something positive. We see that before total aggregate capital was constant, and then we increase population and it shifts up. Similarly down here for output. For these variables, like capital per worker, output per worker, investment per worker, consumption per worker, we see that an increase in the population growth doesn't change the growth rate of those variables, right, because they're per worker, but it does have a level effect on them. So let's see what happens to those through time. So this is capital per worker, and this is output per worker. So we see that an increase in the population growth has a negative effect on the negative level effect on capital per worker and output per worker, and we see exactly that happens. So before population growth was 0, so that's this section over here through time, and then right at this moment in time we have the increase in the population growth, and so we have a level effect. So the first thing to notice is it's not an instantaneous move, it's something that goes through time. And then the second thing is, well, we see that it's obviously shifting downward. So how do we know it's a shift downward? Well, first off, if you were to memorize this whole chart, which I don't doubt, you can see that it has a negative effect here. But secondly, you could actually just turn to the Solow diagram, right? And what happens when we increase the growth rate? Well, if you increase n, that increases the slope of this blue line, so this blue line shifts upward, that's the break-even investment line, shifts upward, and if this blue line shifts upward, we result in a new steady state level of capital per worker that shifts down, which we see exactly here. We also see with output per effective worker, controlling for ligand pair augmenting technology. So yeah, those are the big two effects. There's the level effect, where the growth rate hasn't changed. You're at one growth rate here, and you shift up to a new growth rate there. The growth rate hasn't changed, but you have shifted to a new level. So the process from this point up to about this point, when we're at the new level, you can see that growth did go up faster here, but it then converges to the same growth rate as it had before the shock, right? So that was with something like change in savings. The other type of effect, right, could be an effect on the actual, the overall total growth rate. So with this particular example, you were at some growth rate over here, and then we change something that increases the growth rate, and so we see a shift in the growth rate upwards. So those are the kind of two big effects. And how do you know which one affects? How do you know which one results in a level effect or a growth rate? Well, it entirely depends on the variable you're talking about. So yeah, hopefully that was helpful. If you have any questions, let me know. I think I'm going to go through an applications section, like several examples, to help clarify everything. Thanks and have a good day. If you found it useful, be sure to give it a thumbs up.